Hello guys, so welcome back to our discussion about NAND and NOR gates. And now it's time to discuss the last property, or the last important piece of information about these two new gates, NAND and NOR. So basically, the question is, now we knew their properties, we knew that we can implement any other logic gate using NAND, we can even make a whole design, digital design using just this kind of new gates, either OR, NOR, or NAND. Okay, but some of our designs need some gates that has more than two inputs. So far, we just discussed the two input NAND gate, right? For OR and AND gates, we can extend the number of inputs to more than three. And the reason behind it is that for any function to have, or any logic gate to have that ability to be able to have more than two inputs, is that it should have two basic properties. It should be the associative and the cumulative properties should be satisfied for such gate. So for example, for AND or for OR, whatever, X or Y equal to Y or X. So this is the cumulative property. Okay. And for the associative, and this is the most important one, is that X or Y or Z, if we make ORing for X and Y, then we OR with Z, this will be equivalent to ORing Y and Z, then OR X. The result will be ORed with X. This is the associative property. Okay, and both are satisfied for both AND and OR. How about NAND and NOR? We want to have it. We want an NAND gate that has more than two inputs. Okay, so let's check. Let's check first the cumulative property. Okay, so X, for example, for NOR, X nor Y equal to X or Y, and then the total will be complemented, or the complement of X or Y, which is equal to X bar dot Y bar. Good. Then Y nor X equal to Y or X complement, which is equal to Y bar dot X bar, which is basically equal to X bar dot Y bar, right? Because the AND is cumulative, right? So we can change or interchange the order. So the cumulative property is satisfied for both NOR, and we can prove the same for NAND. For NAND, let's do it together. For NAND, X NAND Y equal to XY complement, which is X complement or Y complement. Y NAND X equal to YX complement, which is Y complement plus X complement. And those are equivalent or equal. But how about the associative one? Okay. Just forget about the analytical solution or the analysis. Just look at the diagram here. So this is basically X nor Y, then nor Z. Okay, this is X nor Y nor Z, but we will do X nor Y first. Okay, so this will give us what? It will give us X or Y complement, and here is, this is Z. This is a typo in the book, and this is Z. Okay, then the output here is Z or X or Y complement, then the total is complement. And by De Morgan's, this will be Z complement dot X or Y. Okay, let's do now X nor Y nor Z. And let's see. So here is X. This is will be Y nor Z. Or let's do it, Y or Z. Y or Z complement. Then the output here is X or Y or Z complement, and the total is complement, which is X complement plus Y or Z. I'm sorry, dot Y or Z. And that's basically different from this. These are not equal. That's basically the proof here. But on the circuit itself. So the associative property is not satisfied for NOR, and we can prove the same for NAND. Okay, so by the current definition, okay, we cannot extend NAND and NOR to have more than three inputs. Okay, because the associative property is not satisfied. So the idea is to extend. This is this is a thing here that you should be flexible with. So just extend the definition. Okay. So we're gonna make the definition of NAND and NOR to be just not and whatever the number of inputs of the AND gate, and NOR is a complement of OR whatever the input of the OR gate. Okay, because the current definition is restricted to AND or OR with two inputs. So just extend the definition of NAND and NOR to be generally the complement of any number of inputs. Okay, that's the basic definition now, or the extension definition now. Okay, and based on that, we can have we can also make a new or we can extend the symbol that we have. The symbol now can have 3 inputs for NOR or 3 inputs for NAND, and we will do just the same. So here we OR all of them together, then we make the complement. Here we AND all together, then we take the complement. Okay, but that was essential to know that we cannot just say okay, NAND is you can have 3 input NAND or 4 input NAND. No, you can't do that directly. You should first look at the math and let the math decide on that. If the math didn't agree with you, then you should extend the definition. Okay, the definition was that if you have an AND gate with 2 inputs, then NAND is not of the output of this AND gate. So make just the definition, general. Any AND gate with any input, number of inputs. Okay. So that's basically the associative property for NAND and NOR. Now the most important question now: do we have a circuit that have 3 inputs that can do that? Yes. The answer is yes. Okay. So basically, you cannot have two. The main the bottom line here is that when you try to do an AND gate that has 3 inputs, don't do it as 2 NANDs, just like this. That's not the correct way. But you should have a circuit that can do that for you, and for that, under that condition, we have. Okay. For AND gate, assume that you don't have a circuit that can do AND gate for 3 inputs. Then you can get 2 AND gates. Okay, one has 2 inputs, and then the other one have another 2 inputs, which would be the output of the first one and the third variable. That's okay. And if you have a circuit, an AND circuit that have 3 inputs, that's also okay. For NAND, no. For NAND, you must have a circuit that has 3 inputs. You cannot construct an AND, a 3 input NAND, from two input NANDs. just like what we did with AND. Same for NOR. So for OR, you can have a circuit that has 3 input and make the function of OR. Or if you don't have, you can get 2 OR gates. Each one has 2 inputs. Okay, and construct them something like this, such that you OR 2 variables together, then the output will be ORed with the third variable in the second OR. But with NOR, no. With NOR, if you have 3 variables that will be NORed together, you must have a circuit or the logic gate or the logic circuit for NOR that deal with 3 inputs. You cannot construct a 3-input NOR gate from 2-input NOR gates. No, you can't do that. So that's basic, bottom line here. So that's all for NAND and NOR gates. And in the next video, we're gonna explore another, interesting gates, which is XOR and XNOR gates. So see you in the next video. Bye-bye.